welcome to G Fun Facts Online. For centuries, humanity looked up at the night sky and imagined a silent, empty barrier. A vast expanse of absolute nothingness, separating our rocky planet from the fiery furnace of the sun. We believed Earth was a closed system. We thought the shifting of our tectonic plates, the terrifying rumble of earthquakes, was dictated entirely by the slow, churning convection of magma deep beneath our feet, completely isolated from the cosmos above. But as our observational tools have grown more sophisticated, a radical and breathtakingly interconnected picture of our solar system has emerged. The Earth is not an isolated rock. It is suspended in a highly reactive, electrically charged web woven by our host star. Today, we are diving deep into the cutting edge of a fascinating, dual-natured field that bridges astronomy and geophysics called Solar-Terrestrial Seismology. This discipline investigates the profound acoustic and kinetic forces triggered by solar flares, which are the sudden, massive detonations of magnetic energy on the sun's surface. What scientists have discovered is essentially a tale of two quakes. When a solar flare erupts, it can strike the solar surface with such immense force that it causes the entire star to ring like a bell, generating literal sunquakes. Minutes later, the electromagnetic shockwave from that very same flare washes over the Earth, violently disturbing our upper atmosphere. Now, in a highly controversial but deeply compelling frontier of modern science, researchers are proposing that this atmospheric disruption can reach deep into the Earth's crust, acting as the invisible final trigger for terrestrial earthquakes. This is the story of the flare connection, a journey of acoustic shockwaves spanning millions of miles, linking the explosive death of solar magnetic fields to the sudden, violent shifting of the ground we walk upon. To understand how a solar flare can crack the crust of the Earth, we must first look at how it cracks the surface of the sun itself. The sun, of course, is not a solid object. It is a roiling, boiling sphere of superheated plasma. Since the early 1960s, scientists studying helioseismology have known that the sun is trapped in a constant state of acoustic vibration. Convective motions of hot gas bubbling up from the solar interior create ambient sound waves, causing the entire star to undergo periodic up and down movements. It vibrates exactly like a ringing bell. By analyzing the Doppler shifts of the light emitted by the sun, scientists can track these vibrations and image the star's interior, exactly as geologists use seismic waves to map the inside of the Earth. But while the sun's ambient hum is relatively gentle, the acoustic violence unleashed by a solar flare is apocalyptic. A solar flare occurs when twisted, stressed magnetic field lines in the sun's corona suddenly snap and reconnect. This magnetic snapping releases an energy equivalent to millions of nuclear bombs detonating simultaneously. The energy radiates outward as blinding light, intense X-rays, and high-speed particle beams. Back in 1972, astrophysicist Charles Wolfe first suggested that this explosive release might send acoustic noise crashing down into the solar interior. However, it was not until 1998 that researchers analyzing data from the Solar and Heliospheric Observatory discovered the first definitive visual evidence of a sunquake. They were observing a moderate X-ray flare that occurred on July 9, 1996. The impact of the flare's energetic particles penetrating the lower solar atmosphere generated a massive hydrodynamic shockwave. The result was absolutely spectacular. Imagine a ripple on the solar surface towering 3 kilometers high. This immense seismic wave accelerated to a blistering speed of 50 kilometers per second, propagating outward to a distance of 120,000 kilometers from the flare's epicenter. Yet, as scientists gathered more data over the years, a mystery emerged. The vast majority of solar flares, even incredibly powerful ones, are seismically inactive. They do not generate sunquakes. It appears that the intense magnetic fields of certain active sunspot regions can alter or absorb the downward force, preventing the wave from propagating. This makes acoustically active flares a rare and highly prized phenomenon for astrophysicists to study. One of the most powerful and illuminating sunquakes ever recorded occurred on January 15, 2005. Originating from an X-1.2 class solar flare in an active sunspot region known as Arkansas 10720, this event was analyzed using an advanced technique called helioseismic holography. This allowed scientists to actually image the seismic waves as they dove into the solar interior and refracted back to the surface. The sheer scale of the energy transfer was staggering. The flare produced an estimated 2 × 10 to the power of 23 joules of visible continuum emission, and the resulting seismic wave carried roughly 4 × 10 to the power of 20 joules of energy. Interestingly, the 2005 event lacked the signature of heavy, high-energy proton beams. Previously, these beams were thought to be the primary physical hammer that struck the solar surface to cause a quake. Instead, the intense seismic response strongly supported something called the back-warming hypothesis. This theory suggests that the lower layer of the sun's atmosphere, the photosphere, is rapidly heated by the intense edge radiation coming from the flare in the layer above it, the chromosphere. This sudden, localized boiling creates a massive expansion of gas. It is a hydrodynamic explosion that violently kicks the solar surface, sending acoustic waves plunging tens of thousands of kilometers deep into the star. As the sunquake ripples fade into the churning plasma of the star, the radiant energy of the flare is already hurtling through space. Moving at the speed of light, X-rays and extreme ultraviolet radiation cross the 93 million miles to Earth in just over 8 minutes. When this intense radiation slams into our planet, it is intercepted by the ionosphere, a thick layer of electrically charged gas sitting roughly 250 miles above the Earth's surface. Now, for generations, the idea that weather, whether terrestrial or space-based, could trigger an earthquake was heavily dismissed. It was relegated to the realm of myth and pseudoscience. The United States Geological Survey has long emphasized that earthquakes do not follow the sun's 11-year solar cycle in any clear, repeating way. In fact, a comprehensive 2013 study published by USGS researchers analyzed earthquake databases spanning from 1900 all the way to 2012. By comparing the occurrence of large earthquakes against records of sunspots, solar wind velocities, and geomagnetic activity indices, the researchers used strict statistical testing, including chi-square and students' t-tests, to look for correlations. They found no consistent or statistically significant distributional differences. They firmly concluded that the null hypothesis of no solar terrestrial triggering could not be rejected. But science is a continuously evolving dialogue. Fast forward to February 2026, and a groundbreaking, albeit highly controversial, study published in the International Journal of Plasma, Environmental Science and Technology by researchers from Kyoto University radically reopened the debate. The researchers are not claiming that solar flares possess the raw mechanical power to move tectonic plates. No solar flare is physically pushing a continent. Instead, they propose a highly specific, electrically driven tipping point. Their model suggests that a solar flare can act as the final straw that breaks the camel's back for a fault line that is already critically stressed and on the precipice of rupture. Ken Umeno, the senior author of the study, stated clearly that they are not claiming solar flares generate tectonic stress. Their argument is entirely about timing, not energy. When a fault is already close to failure, even a microscopic perturbation may shift exactly when that rupture occurs. So how does a burst of light in the upper atmosphere reach miles underground to snap solid rock? The proposed mechanism relies on treating the entire Earth as a massive electrical circuit. When a powerful solar flare hits the Earth, its intense radiation rapidly ionizes the upper atmosphere. This sudden surge forces the electrons in the ionosphere to move downward, shifting the electrostatic balance and concentrating a layer of negative charge at lower altitudes. Satellites monitoring the upper atmosphere record this as a massive spike in total electron content, or TEC, with values sometimes jumping by several tens of TEC units. This heavily charged ionosphere weighs down the localized environment, not with physical mass, but with electrostatic charge. Below the surface, the Earth's crust is not a completely solid, uniform block of stone. It is riddled with microscopic voids, cracks, and highly fractured fault zones. Deep within these fault zones, groundwater exists under extreme temperatures and pressures, often in a supercritical state. Electrically, these fluid-filled fractured zones can act like massive natural capacitors. According to the Kyoto University model, the crust capacitor and the charged ionosphere are linked by an invisible electrical field. They operate exactly like two ends of a giant leaky battery. Through a process known as capacitive coupling, the dense buildup of negative charge in the lower ionosphere creates an intense electric field that penetrates the microscopic voids of the fractured rock below. The resulting electrostatic force exerts literal, physical pressure on the surrounding rock. The researchers calculate that the ionospheric disturbances tied to major solar flares can generate electrostatic pressures of several megapascals within these crustal voids. To put this in perspective, these pressure changes are mathematically comparable to the subtle but persistent gravitational and tidal forces exerted by the Moon, which geophysicists already recognize as a secondary factor that can influence fault stability. If a tectonic fault is relatively stable, a fluctuation of a few megapascals of electrostatic pressure will do absolutely nothing. The rock will hold. But if two colossal tectonic plates have been grinding against each other for centuries, building up unimaginable mechanical strain, they eventually reach a state of critical stress. At this razor's edge, the fault is hanging by a geological thread. The sudden introduction of electrostatic pressure inside the rock's microscopic voids might just provide the minuscule nudge required to overcome the final barrier of static friction, triggering a catastrophic rupture. To support this provocative theoretical model, proponents point to a series of recent, high-profile seismic events that align eerily well with intense space weather. The most prominent example cited in the 2026 literature is the devastating magnitude 7.6 Noto Peninsula earthquake that struck Japan on January 1, 2024. This massive rupture occurred barely a day after one of the strongest solar flares of the decade, the most powerful of 2023, battered the Earth's atmosphere. Researchers noted that the intense solar flare activity drastically altered the ionospheric electron density just as the critically stressed fault in the Noto region gave way. Other clusters of events add heavily to the intrigue. The researchers highlighted a separate earthquake in December 2025 that closely followed another intense flare, as well as minor quakes in high-latitude zones during a February 2026 swarm of space weather. Historical echoes have also been re-examined. Take the catastrophic 2011 Tohoku earthquake. Some studies now suggest this event synced with unusual solar radio noise and ionospheric anomalies. Observers have long documented unusual ionospheric behavior, such as drops in ionospheric altitude, spikes in electron density, and slower propagation of medium-scale traveling ionospheric disturbances in the days leading up to powerful earthquakes. While traditionally interpreted as the stressed crust leaking electromagnetic energy upward into the sky before a quake, the new model suggests this could actually be a two-way street where the sky is actively pressing down on the crust. Despite the elegant mathematics of capacitive coupling and the poetic symmetry of solar-terrestrial seismology, the broader geophysical community remains highly skeptical. The primary counterargument is a statistical one known as the coincidence problem. Solar flares, especially during the peak of the 11-year solar cycle, are incredibly common. Minor and moderate earthquakes are happening constantly around the globe, and even large earthquakes occur multiple times a year. As a matter of sheer statistical inevitability, some large earthquakes will happen on the exact same day as a large solar flare, even if the two systems are entirely independent of one another. Nicholas Schmer, a geophysicist at the University of Maryland, reviewed the 2026 findings and described the paper as highly speculative. Schmer pointed out that far more robust evidence is required to prove true physical causality, rather than mere temporal overlap. Similarly, Viktor Novikov, a geophysicist at the Russian Academy of Sciences, critiqued the Kyoto University model for failing to capture the immense, messy complexities of the Earth's crust, noting that the proposed model is greatly simplified. The scientific barrier to proving this hypothesis is absolutely immense. Validating a direct, real-time electrical connection between a fleeting patch of ionized gas 250 miles in the air and a grinding tectonic plate 10 miles underground is, with our current technology, practically impossible. While the math allows for electrostatic pressures of several megapascals to exist in supercritical crustal voids, mapping those microscopic voids and measuring that pressure precisely at the moment a fault ruptures remains far beyond our grasp. Until predictive success can be consistently demonstrated, many geologists will continue to point back to the USGS's 2013 findings. For them, historical data simply does not show a statistically significant footprint of the Sun controlling terrestrial fault lines. We are currently navigating the chaotic peak of the 11-year solar cycle in 2026, Satellites like SWARM and GOES are tracking coronal mass ejections and flares daily, providing scientists with an unprecedented volume of data to test the Kyoto model. If Kenya Mano and his colleagues are even partially correct, the implications for human survival are profound. Earthquakes remain one of the most devastating natural phenomena precisely because they cannot be reliably predicted. If critically stressed faults are indeed sensitive to sudden spikes in ionospheric charge, monitoring total electron content anomalies could eventually become a crucial variable in short-term earthquake risk assessment. We might one day look to the violence of space weather not just to protect our power grids and satellites, but to gauge the imminent danger deep beneath our feet. Regardless of whether the electrostatic trigger hypothesis holds up to decades of future scrutiny, the overarching paradigm of solar-terrestrial seismology has forever changed how we view our place in the cosmos. We know for an absolute fact that the magnetic fury of a solar flare acts as a mighty hammer, violently striking the solar photosphere and sending 120,000-kilometer-wide acoustic ripples plunging into the heart of the sun. And we know that the ghostly electromagnetic echo of that same event violently reshapes the electrical ceiling of our own world. From the roaring acoustic depths of a star to the silent, supercritical fault lines deep within the Earth, the solar system is not a collection of isolated spheres. It is a deeply interconnected instrument, continually resonating with the energetic outbursts of its central star. And as we continue to listen to the seismic echoes across the void, we are learning just how tightly our rocky world is bound to the fires of the sun. Thank you for listening to G Fun Facts Online.